All right, so today we are starting related rates. These are rates that are related to each other, hence the name related rates. We are going to use some implicit differentiation with this. All right, so I'm going to explain to you, and there's a very precise process. I don't know if precise is a good word, just an organized process for this, and if you do these parts that I'm telling you to do, you'll be able to organize them all, and it will all be fine, okay? So we have a related rates problem, and this is what it's called, related rates. Involves at least two changing quantities. Okay, so two things are going to change, not just one. It's not like X changes and then we get Y, that kind of thing. Where the rate at which one quantity changes affects the rate at which the other quantity changes. So it's still a dependent type of relationship, but it's the rate of change that changes, right? And we understand that a rate of change can change. That's why we have that instantaneous rate of change, right? So the first thing we're going to do is we're just going to translate some sentences. So let's translate the sentences into proper calculus notation to identify the information. All right, so number one says the area of a circle is increasing. So we're talking about area increasing at a rate of 6 square inches per minute. So if the area of the circle is increasing, that means we're talking about the rate of change of the area, right? And we find rate of change by taking the derivative. So the derivative of area with respect to time would just be dA dt, right? The derivative of the area with respect to time, that would be the rate of change of area. Make sense? That is equal to 6 square inches per minute. And you can look at your units here. Inches squared is area, your time is minutes, and that's what you have right there. It's how area changes with respect to time. We good on that? We've got to make sure we understand the wording here with this. All right. So let's look at number two. We're looking at the volume of a cone is decreasing at a rate of 2 cubic feet per second. So if we're talking about the rate of volume, that's dV dt. The rate of change is 2 cubic feet per second. How do we show that it's decreasing? It's a negative rate. Right? Okay. So increasing is positive. It is what it is. Decreasing would be negative. Okay. We okay with that? Make sense? All right. I'm going to give you a minute. You write something for number 3. He's really fired up about whatever they're talking about today. Okay, so the water level in a fish tank is decreasing. So I'd have d something dt. But I have to have a something in here. What do you think that something could be? W, okay? Anybody have anything other than W? L? What? I heard W and I heard L. What else? Anything? Anybody have anything else? F for fish tank? Ooh, that would be tricky. Yeah, okay. Can't be T, but it really could be anything. Whatever makes sense to you. If you did DW, if you did DL, L for level, W for water, okay, that's okay. I'm going to put, and you don't have to change, well, maybe just write this next to it. I'm not saying, or make it equal. I'm not saying that yours is, well, it's not equal, it'll be the separate one. I'm not saying that yours is wrong, but let's think, what is the water level? Let's say, we don't really know what the fish tank looks like. It could be like one of those round goldfish tanks, but let's just say it looks like this because I can draw this quickly. And it's not even that great, but okay. So let's say that we have a rectangular fish tank that looks a whole lot better than that. So the water level in there, wherever the water level is, right? If this is my water level and it's decreasing as far as a prism is concerned, what's that? What's that? Okay, so it's the volume is decreasing, we know that, but the water level itself what gives you the level? What changes here? Height. Okay, does that make sense? So, like I said, if you have W for water, L for level, totally fine. I'm going to put DHDT because it doesn't say what you have to use, and you can use different things depending on what it is. We're going to do one of these where we use a different variable than what the formula really even says, and I'll explain why we get there. So this is equal to what? -2 inches per hour, exactly. Okay? But you have to have something, whether it's height, whether it's W, whether it's L for level, all those are fine. Okay? So the volume is also decreasing, but the volume, let's think about this, the volume is going to decrease at a different rate than the height is. You with me on that? Okay, good deal. All right, so this is all with respect to time. Okay, if we're talking about a rate, your rate has some sort of time aspect to it. So we're going to do implicit differentiation. And instead of where we were doing dy dx and we were doing everything with respect to x, we are going to differentiate these with respect to time. Okay, so when I do this one, I have so it says use implicit differentiation to differentiate with respect to time in order to determine how the rates of change of variables within the equation are related. So here I have circumference and I have a radius. Those are going to change at two different rates. Okay, so when I do my implicit differentiation, that means I'm going to do d dt, right, of the whole thing. So that means I get the derivative of c is just 1, then it's dc dt equals the derivative of 2 pi r will be 2 pi. I took the derivative of r, so that's dr dt. Okay? Whereas when we did this with x and y, we kind of left the dx off. We didn't really leave it off, but dx was 1. So you're going to have one of these stuck to every single variable, and they're going to be different, and it's fine. Okay? Do you see how that works? All right. Y'all do this next one. Let's see what we get. I'm going to give you a second to do that one, and then I'm going to make sure we get it, and I'm going to let you do the rest. You good? So when we take the derivative of a, it's just 1, but since we took the derivative of a, that's dA dt. So it's basically like 1 times dA dt equals 2 times pi times r, right? And then that I took the derivative of r, so that's dr dt. Okay. What questions do you have about the process? Does that make sense? Okay, so I'm going to give you a little bit of time, and I want you to do the rest of them, see what you come up with. Think about some of the rules along the way that you might need to use. You can simplify. Although you're missing something in that one. Think about what you're missing. What's the derivative of this? Not just 2. What do you do with an exponent? Yeah, you bring the exponent out front. Yeah, yeah. What rule are you going to use as you do this? Not the chain rule. What do you mean it's not a negative one? I'm not sure. No, no, you're still missing something. What's the derivative of a squared? But it's not just, the derivative of a squared is not 2. 2a. Okay. So you use the product rule here, but you didn't use it here. Why is that? Is that a product also? Yeah? Yeah? Okay. It's about the variables. So like you can use r squared and h. So you can do a couple of different things with the 1/3 pi. You can either stick it to the r and keep it along with the r, or you can bring it out in front, whichever makes the most sense to you. That, yeah, and 1/3 pi, and then open your parentheses, and then just take care of r squared times h. That works. I mean, there's different ways to do that. Mm-hmm. We can only take out the 2, yes. Two-thirds pi r. Yeah, but, okay, so when you do this part, you took the derivative of something with r in it, right? So you need a dr dt and then times h. What are we confused on? What rule do you have to use on that one?
This one?
Yep. So what she has is not correct.
Oh, I know.
Oh, she's not finished.
Yeah.
Okay. The second.
What's the derivative of L?
Yep.
This one just cancel out, right?
Yep. Yeah, so you can do 2 different things with this 1/3 pi. You can either stick it to the r squared and use it like that, or you can bring it out front and then take the derivative, whichever one makes the most sense to you. I'll show you both when we do it. But so I probably would just stick it to the r squared if it were me, but. Okay, so the derivative of the first times the second, okay, plus the first. Well, if you used this 1/3 pi, you stuck it to r squared and used it when you took the derivative, so it's still stuck to the r squared. Or that works too, except you don't have a, when you did that, the 2r, you have to have a dr dt in there. Okay. So far, you're not finished, but yes. That's the derivative of the first times the second, plus, this is the product rule. The derivative of plus the first times the derivative of the second. The product rule, the derivative of the first times the second, plus the first times the derivative of the second. Plus, what's the first? 1/3 pi r squared times the derivative of the second. Yes, and then the times the derivative of h. Oh my God, that is not long at all. That looks good. Yeah, you can do it like that. It's fine. Okay, so let's talk through these. If I'm going to take the derivative of this one, that's going to give me dv dt. Even though things are being multiplied, I do not have to use the product rule because I only have one variable. So I do 3 times 4/3, which gives me 4 pi r squared dr dt. Okay. Everybody okay with that one? Well, on the third one. The first one you did on your own, but yeah. Yes? Okay. So let's move on to this one. So no, I took 3 times 4/3 gives me 4 pi r squared, and then dr dt. There's no product rule there or anything. Okay. All right, so this one, the derivative of a squared is 2a, and then that's times dA dt, the derivative with respect to time, plus the derivative of b squared is 2 times b db dt equals 2 times c dc dt. Okay. Everybody good with that so far? Can we simplify this one? Yes, I can divide the whole thing by 2, so those all cancel out, and I really just have a dA dt plus b dB dt equals c times dC dt. Okay? It's not wrong the first way, but when we apply it, which we will have one of those that we'll look at, it's just easier not to have to multiply things by 2. Right? We good? All right. So then let's look at this one. Here, I have 2 variables being multiplied together, so I have to do the product rule. So this will be dA dt equals the derivative of the first, so the derivative of L is dL dt times the second, which is W, plus the first, which is L, times the derivative of the second, which is dW dt. Okay. What questions you got? We agree with that? What did you do? Cameron, I'm going to make you sit at a table by yourself. Okay, I'm going to work this one 2 different ways, right? There's 2 ways to handle this. First of all, either way, you have to do the product rule because I have 2 variables being multiplied together. So the first way I'm going to work it is by taking this constant, the 1/3 pi. So this will be dV dt. And that's equal to, I'm going to put this 1/3 pi out here and then open my parentheses. So if you didn't do it this way, just write it down so you know there's another way. What you did isn't necessarily wrong. I'm taking this out, and then I'm going to multiply it by the derivative of that. This requires the chain rule. The derivative of the first, which will be 2r dr dt, times the second, which is h, plus the first, which is r squared, times the derivative of the second, which will be dh dt. Okay? That's one way to handle it. Another way to handle it, and it's a matter of opinion here on which one you like better, is instead of putting the parentheses there, I could kind of put the parentheses here. So I'm going to have that 1/3 pi stuck to the r squared, so that when I do dV dt, when I take the derivative of the r variable, I'm going to take 2 times 1/3, which gives me 2/3 times pi times r dr dt. So that's the derivative of the first times the second, which is h, plus the first, which is 1/3 pi r squared, times the derivative of the second, which is dh dt. It's the same thing. This one is just if I took this 1/3 pi and distributed it, and then if I took 1/3 pi and factored it out of this, I would end up here. So really, I mean, it's the same. Whatever makes the most sense to you is fine. Get the same thing. What questions we got? We good? Okay, so let's apply this. So here's how this works. We have to read the question. We may have to read it more than once. But this says a pebble is dropped into a calm pond, causing ripples in the shape of concentric circles. The radius of the outer ripple is increasing at a constant rate of 1 foot per second. The radius of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, find the rate at which the area of the disturbed water is changing. Okay? So, that's what you're going to think when you read a lot of these. You're going to read it and you're like, what the heck did I just read? So we go back and we figure out, what is it that I'm even looking for? It says, find the rate at which the area of the disturbed water is changing. So I need the rate at which the area is changing, dA dt. I don't know what that is because that's what I'm looking for, so I'm going to put a question mark. I'm also going to go ahead and put my units. So this is in feet. So area is feet squared per second. That's what the units will be on that. So from dA dt comes from the area. Was I given the area? I was not given the area, so I don't know that either at this point, and it's going to be feet squared. Okay? So let's figure out what we know. It says the radius of the outer ripple, so that's like the biggest part, is increasing at a constant rate of 1 foot per second. So dr dt, that's the rate at which the radius is changing. That is 1 foot per second. So since I did dr dt, I need to see if I know r. So r is changing, obviously, but the question is asking me about what happens when the radius is 4 feet. So I have 4 feet right there. Okay? If you write down a rate that you are looking for, make sure you have so if it's the derivative of area, that you have area and either a question mark or you have a variable. The derivative of the radius, and then you have the radius, whether it's a question mark or a number that we know. Okay, we all good so far? So since I'm looking for dA dt, I need to go ahead and take the area formula, which this is the area of the circle. It is pi r squared. That is not something you will be given. You have to know how to find the area of a circle correctly. So we take this derivative with respect to time. Okay? So this becomes dA dt equals 2 pi times r dr dt. Okay, everybody with me? Now, let's substitute in what we know. Well, this is what I'm actually looking for in the question, so I don't know that. I know, well, 2 pi, those are constants. I know the radius that I'm supposed to be using, and I know the rate. So dA dt, oh, I wrote the wrong thing. dA dt, oh my goodness, what is wrong with me? dA dt is equal to 2 times pi. Whew. Once I get off track, my brain just does not get back on. Okay, times 4, and then the rate is 1, which means that dA dt is equal to 8 pi, and I don't even have to think about the units. I already wrote them down. That is feet squared per second. That's the answer. If you actually list out what you know and what you need to know, and you're consistent with that, you will have all the pieces you need every single time. Okay? And related rates come up a lot, and they can be very confusing for some people, but the consistency is the key here for sure. Okay? Not skipping things and thinking you don't need to write it down. Okay? We good so far? All right, so let's look at this next one. So I'm going to read through it. The volume of a sphere is increasing at a constant rate of 4,500 cubic inches per minute. At the instant when the radius of the sphere is 15 inches, what is the rate of change of the radius? And this time they will give you the volume of a sphere formula, they'll give you the volume of a cone, and they'll give you the volume of a cylinder. Everything else you're expected to know. Okay? So we are looking for, go back, what is the rate of change of the radius? That means I am looking for dr dt. Since I know that that's what I'm looking for, I definitely don't know it. But I'm going to look at my units here. The radius, the units are inches. Time, my units are minutes. So with dr dt, r goes along with that. And it says at the instant when the radius of the sphere is 15 inches. So this is 15 inches. So the other things it's talking about, the volume of the sphere is increasing. So the rate of this volume is dv dt. That is increasing at a rate of 4,500. And that's cubic inches per minute. Do I know the volume at that point? I do not, right? So I don't know that. And I don't necessarily need to find everything that I have a question mark for, but you will find that in some cases you do, and you want to kind of have it all lined out there. Okay, we good? All right, so now that I've written down what I know and what I'm looking for, my formula, volume is equal to 4/3 pi r cubed. I take the derivative with respect to time. That's going to give me dv dt is equal to, so that will give me 4 pi r squared dr dt. Okay. Everybody good so far? All right, so I'm looking for dr dt. Let's just start substituting stuff in. Do I know dv dt? Yes, it's 4,500. That's equal to 4 times pi times, do I know the radius? Yes, that's 15 squared dr dt. Okay. Now, do I have to actually square the 15 and do all that stuff? I don't necessarily have to. What am I looking for? dr dt. Can I divide both sides by this right here? Yes, so I can say 4,500 divided by 4 pi times 15 squared. And dr dt, my units I'm getting from over here, inches per minute. That is equal to dr dt. Before we go any farther, make sure you understand where everything came from and why. Kylie, did you have a question about something? We're all good. Everybody understand where everything came from? Okay, so this is a safe stop. But sometimes we have to simplify it. That does not mean that I have to multiply, I have to square 15 and multiply it by 4 either. I'd like to reduce that fraction. So isn't 15 squared just 15 times 15? Yes? Okay, so we're going to reduce this a little bit at a time, just so I can show you what you can do here. So I can take 4,500, and I know that 15 goes into 45 3 times, right? So if I just take 4,500 and divide it by 15, doesn't that leave me with 300? So then I still have down here 4 times pi times 15, right? Because I used one of the 15s. Doesn't 15 go into 30 twice? So that leave me 20 in the top over 4 pi. And then that just reduces to 5 over pi inches per minute. So work smarter, not harder when you're having to simplify things. But remember, you don't, if this was a free response question, you could stop here. But even in a free response question, there may be a reason you want to go farther, especially if you had to substitute it back into something else. So just know how to manipulate numbers so you're not, because otherwise you have 225 times 4, and then that's over 4,500, and then you have to reduce that crazy fraction, and you know. So there's other ways around things. Okay. What questions you got? Okay. Let's look at this next one. So this says the top of a 25-foot ladder is sliding down a vertical wall at a constant rate of 3 feet per minute. Okay. when the top of the ladder is 7 feet from the ground, what is the rate of change of the distance between the bottom of the ladder and the wall? Okay, so I want you to also think about this, because this is like a basic related rates problem. If I've got this ladder, let's see, this is going to start where I wanted it to. Okay. So I can't actually slide this like I want to, but when it started, where's the pop-up for me? Oh, it's down here. It's just a ladder. It's just a ladder. Okay, so at 2 seconds, this is being pulled away at a steady rate of 1 foot per second, or 1 meter per second, whatever this is 1 foot per second. So so I'm at 2, I'm barely down off of 10 off the wall, right? When I get to 4, or 4.5, I've only gone down 1 foot off the wall. When I am at, let's go to 8, well, it won't stop. Stop! Okay, anyway, did you see how it looks like it's speeding up? Okay, this is a constant rate, but it's speeding up as it goes down. Have you ever, like something sliding down the wall and you go to catch it, and before you catch it, it hits the ground and you feel like it sped up? Because it probably did speed up. That's what's happening here. Even though we are doing this at a constant rate, even though one part is constant rate, the other part is not. So in this case, with a ladder problem or with some of the others, if you read this stuff and maybe it makes sense to you, maybe it doesn't, we're going to draw a picture. Okay? So here's our picture. Here's our picture. Okay? We're going to make this A, B, and C, because it's just a right triangle. Okay? You with me, Lorenzo? All right, so the top is sliding down the wall at a constant rate of 3 feet per minute. When the top of the ladder is 7 feet from the ground, what's the rate of change of the distance between the bottom of the ladder and the wall? All right, so there's the change in all of these. So we want, dA dt, because this is my ladder, right? You can do this if you want. There's my ladder. It says the top of the ladder is sliding down a vertical wall at a constant rate of 3 feet per minute. So this is 3 feet per minute. Oh, and it would be -3, thank you. And then this is, and then A, I don't know what A is, but it would be in feet. Okay. So B is, as this slides down, B is moving this way, yes? So there's a rate of change for B, so dB dt, I do not know, but that would also be in feet per minute. Okay. Oh, actually I do know A, because it says when the top of the ladder is 7 feet from the ground. So instead of a question mark, this is actually 7 feet. I do know that part. Okay, but I don't know, so that your numbers come out nice. But I don't know B at this point, so that's a question mark with a feet. dC dt, do we know dC dt? We don't know that. And that would be in feet per minute. Do we know C?
Yes.
What is it? 25. So this is actually 25 feet. As the ladder is sliding down the wall, does that change?
Yes.
No. This changes and this changes, but does the length of the ladder change? No. So what is dC dt? What's the rate at which C changes? 0. The rate at which the length of the ladder changes is 0. Make sense? The length of the ladder is not changing. This length and this length changes. This length does not change. That's why that's 0. You with me on that? Okay. So now we're using Pythagorean theorem. So a squared plus b squared equals c squared. So this is 2a dA dt plus 2b dB dt equals 2c dC dt. Everybody okay with all that? I mean, it's the derivative of the Pythagorean theorem, just like we did on the front. Now, can we simplify this before we move on? Yes, I can divide it all by 2, which might be kind of nice depending on what kind of numbers I have. So this is just a dA dt plus b dB dt. What did we say that, dB dt, sorry. We already said that we knew what c squared was, right? Or c was. This is 25 squared. What's the derivative of 25 squared? Close. It's just a number, right? Or, no, it's just a number. What's the derivative of a number? 0. Plus, we know that this is 0, so that zeroes out this whole thing. This is just equal to 0. Okay, we good? But do you see how you fill that in, and then you have to decide what you know and what it means, right? And we took the derivative. So now let's substitute in everything else we know. We know 7 is a. So 7, and I know that this is times a negative 3. Plus, do we know b? No. Could we find b?
Oh, yes.
How could we find b?
Because we know A, B.
We know it is not equal to 0. We know a and we know c.
You could do the Pythagorean.
You can do Pythagorean theorem. 7 squared plus b squared equals 25 squared. It's the derivative that equals 0, not c itself. It is not 12. I want to make sure you understand why it's not 0. It's the rate at which it changes is 0. The actual length is 25. Well, the end of the equation, we're not at the end of the equation. So once you do this is a Pythagorean triple. B is 24. It's a 7, 24, 25. That's why they gave you nice numbers. Okay, we don't have any crazy square roots. Because 625 minus 49, you take the square root. It's a Pythagorean triple. It comes out. You could do Pythagorean theorem if you need to, but you'll get 24. 625. You really do need to know your perfect squares up to 25 for reasons like this, that you can fly through it quickly if you don't know your Pythagorean triples. Okay. All right, so now I know b. We just figured it out. It's 24. So this is plus 24 times dB dt, which we don't know, and that is equal to 0. Now I only have one unknown, whereas if I hadn't found b, I would have more than one unknown, right? So now you find dB dt. Basic, simple math, two-step equation. What questions you got? It asked me for, let's see, let me make sure I answered the right question. It says, what is the rate of change of the distance between the bottom of the ladder and the wall? So yes, it wants this rate of change, and that is dB dt. So we're good, okay? We good? Yeah. All right. So I challenge you before tomorrow on the next question, draw yourself a picture. It will help. Get this stuff, this kind of stuff written down. Okay, you don't have to work the problem, but see if you can get out of the question what you know and what you're looking for, and we'll start there. That's the one thing I want you to do before tomorrow. We got it? Okay. Do it for real. Miss Bruce is going to be here tomorrow. Impress her.